Right, this video is a quick little video just to whet your appetite with Circuit Wizard. Now you've already used it for your pet feeder project. Hopefully this video will give you an idea of what you could do with it with regard to potentially integrating it into an NEA. So I'm going to show you a few of the features you might not have experienced so far, and then how you might be able to use them, and give you an example of a little kind of project that I made, recreated from an old university project, just to give you an idea, a flavour of the level that you might want to tackle for your NEA. So we'll just go with circuit design. Just in case we want to kind of draw a few components and whatnot. So remember as well, if you go straight into this, you'll find that you've probably got the most basic GNE PIC development board there. So you've got to bring it into the circuit on the circuit diagram to get a GNE 18 or a bigger GNE development board. So all you need to do really is just bring in a where are we, microcontroller here. So it's slightly different to the product design option where you've got a colourful kind of project board. You can wire it up to test the circuitry as well, directly from the PIC. So you would be able to do that in real life, so you can have a smaller circuit rather than having to have a great big GNE development board. But uploading programs to test and prototype, it's easiest just to do it straight off the board. But you can basically design a circuit just having the chip on its own. So you've got two options here. They're both exactly the same. It's just a different schematic way of drawing it. So this is as you see the chip, and this is a slightly more electronic engineered method of drawing chips, where you've got the 5-volt rail at the top and the 0-volt rail at the bottom. One thing you've got to do when you use these, the more advanced kind of circuit design thing without the GNE board, is make sure input 5, where it says R, make sure that is always on high. It's kind of like a reset switch. If it's not high, it's always being reset, so it won't work. So power supply is here. We'll just put a 5-volt battery on this one. So yeah, as you can see, quite often there's a 5-volt rail at the top of the circuit design and a 0-volt rail at the bottom, and it's more intuitive if you use the other one. Just because you can draw the 5-volt and it doesn't tangle up these lines so easily. But on this one, we're just going to do like this. And then, like I said, if this is tied high, put a little protective resistor in there as well. 1K will be fine. And that will just go down to that. So that will now work in real life, but on the simulation as well. And now when you use the digital inputs, you see that you've got the correct number of inputs for that chip. So that's just top tip when doing your own specific circuit design. So with the pet feeder, you'll have come across digital read in, where it checks for an input, easy peasy, sends output to LEDs, or some of you might have got as far as using motors, etc., etc. And then there's wait commands. Some of you might have got a bit more advanced and gone into subroutines. So in other words, lost it here. So you can have a nice kind of long, complicated flowchart here that might repeat itself. So you might create a mini circuit program, that goes on here, and then you can call that subroutine on the main circuit. So if I'd name that one flashlights, for example, then you can call flashlights in your main program when you want the sequence that you've written out here to happen. So if you've got this feature repeating a few times rather than having long strings of flowchart, you can just have a subroutine as well. For loops as well. So if you're repeating something 4 times, 5 times, or something like that, you can say for 1 to 4, do this. This is a really quick kind of brushing over the features. Certainly for the more basic features that I'm covering right now. Don't forget to have a look at another YouTube teacher called Rob Winter. He does some really good program tutorials about basic functions in Circuit Wizard as well. But yeah, a for loop, basically, you can have a sequence of things happening and then end loop, so everything in between these two flowchart boxes will happen 4 times, and then it will come out like that. Instead of counting for number 1 to 4, you can have 10 seconds, for example. So that's quite useful. While is quite a similar one. Well, it's not particularly. These two can be quite similar. While, until. So while, for example, you can either have an input is pressed or not pressed, for example. So while the button's held, do this. Or, and we'll get to analog inputs in a bit, but you can also say while the potentiometer, while the the potentiometer is a certain amount, or your light dependent resistor is within a certain threshold, this part of the program happens. Or you can have variables. So that's another thing we'll get to as well. You can store numbers, whole numbers, in the memory of these chips. So you can count things happening, and while the score is less than 10, for example, in your game, this happens, and then when you get over 10, it will just exit this loop. So those 3 things are quite useful for while loops as well. And so this is while is obviously while something's happening, and then until, it's the same kind of thing, until you kind of reach that threshold as well. So so you can imagine whilst the button is pressed, this happening in a while loop, or for an until loop, this happens until the button's pressed. So the 3 different options of input, or rather compare of values, is also valid for the until loop. So for compare, you might have variable A is less than, and then you could compare it to a different variable, or you could say the score is less than 10, then you get 2 points for everything that happens. Not only that, you can have multiple compares. So while you've got the score of less than 10 and the time is less than 60, for example, you can get a certain bonus. So there's quite an advanced way of kind of tracking and holding and storing onto data, and manipulating that data to be able to do certain functions. The example that I'm going to show you uses a lot of that, so it's quite handy. Obviously we've got outputs and inputs, we all know about those. That's not a very versatile thing compared to just having outputs. So you can have any of the outputs on the PIC chip set to high or low, or you can just set an individual one high or low, or you can just toggle it, as you might have noticed. So you can have it high or low, or you can have it T, which will swap it from what it was. So if it was low, it goes high. This, I haven't really used this much, to be honest, but I think that is okay. To be honest, there's some certain things that I haven't even used, but it looks like you can use and you can look at the input on A1, analog input on 1, and assign it to a variable. I don't know. You'll find there are numerous ways of doing the same thing in these things. Sound we're not going to bother with at the moment, but you can have a tiny little speaker attached to an output, and basically this will send a PWM signal or something like that. It's basically an on and off set of on and off outputs, so fast that they're tuned to the different notes of the scale. So you can play a little tune if you want to do a sequence of sounds or whatnot. So yeah, one of the really useful things with the Genie system is we've got these 16:2 LCD, alphanumeric LCD displays that you can plug into the output. They only need one output. They're sent out on again, like a pulse of data gets sent out on one output. It's called a serial output. And that gets converted on the actual LCD chip, and you can send messages. Now that's really useful for having a bit more user interactivity with the user, make it more user friendly. So press button to begin. For example, you can see the limitation of how many characters you can have on each line. So begin would go on that one. Other things you can do, you can play around with different variables as well. Now what you can do there, for example, let's say I've got a score on the LCD. Now what I would do is use these square brackets and then write A. Now assuming my variable in my flowchart A is the score, whatever that value of that A variable is, it will display it on the LCD. In this case, it's 0. But that's really useful as well. This is the output that you choose it set to, depending on the design of your circuit. So yeah, it's quite a versatile and useful thing, and it just really kind of jazzes up a design project for whatever you want to do. So yeah, really useful thing there. Motor as well. Now we can control ordinary DC motors, stepper motors, and servo motors on these Genie chips. Get to that again in the example project that I'm going to show you. If you've got a motor, let's say connected to M1, if you just had it going one direction, you might just have output 0 connected to the motor, and the other side of the motor would go to 0 volts. So whenever you control the motor to go forwards, it will send 5 volts out to output 0, or it'll open the gate, as it were, to be able to power the motor. Now, as I was saying before, if you're designing your own circuit like that, you can't just plug a motor onto this chip. There's not enough power, there's not enough current available to be drawn from the chip. You've got to amplify it with either, well, if it's a big motor, you might want to have a whole different circuit, let's say, you know, a 12-volt circuit, and then have a relay, for example, which is a mechanical switch. Now, even a relay is too powerful for the outputs of this, so we would have a transistor, for example. We'll just have a standard NPN transistor coming out of output 0, let's say. And then that would be the 5 volts. And then we could either have a little LED or something like that as a signal, but in the case of switching on a big chunky motor, we'd have a relay. So in this case, we just have a SPDT, that's single pole dual throw. So in other words, we've got two, you can either have it on one circuit or on another circuit. So you can have a light on this one and a light on this one. So every time it switches, it goes from light there to light there. All this is just left disconnected, and then it's just simply an on-off switch. So in this case, we might have a motor help me here, motors, electromechanical, I believe, yeah. And then this would be connected to a 12-volt system. So we'd have it 12 volts there. So this might be a nice powerful motor, say a pump for an automatic pond feeder. Or, you know, this is where you can really kind of come up with ideas to potentially do some you know, practical solutions to design problems, as an example. So yeah, think about the hardware. You can use little motors on the Genie chips as well. I wouldn't put a bigger motor on it, but just little tiny motors are able to be powered off the bank of transistors on the Genie development board. So yeah, you've got motor control in forward. I've lost the thing, bear with me. So yeah, there it is. So yeah, if you were to have one motor, now you can have two outputs off your Genie chip. So if it sends a high on output 0, it goes one direction. If it sends a high on output 1, it will go in the other direction. So you can imagine you can have the motor going forwards and backwards like that. And you can control the speed. Now, rather than sending less voltage out to the, obviously a transistor, an amplifier is kind of digital. It'll switch it on or switch it off. So you can't have like dimmable lights, for example. You might think like a 240 volt light when dimmed is only sending out 120 volts. It's sending out 240 volts, it's just pulsating. So in other words, in the same way as this is happening, full power, let's say the output's 5 volts, this is just a steady stream of 5 volts coming out of output 0. But this is a kind of ratio of how much on and off it is very quickly, you know, depends. So there'll be a pulse coming out of it. So say if it's at 5%, only 5% of the time is it on 5 volts, and the motor will turn slowly. So I've used that again in the projects that I'm giving you an example of. Servos are really useful and quite easy to use as well. So again, you only have one little tiny output, and then you have a 5 volt and a 0 volt on it on the servo. So it's powered by the 5 volt and 0 volt, and then the small output on Q0, for example, doesn't have to be amplified so much. It's just a little, what again called a pulse width modulation signal, which controls the position. So here we've got a range from 225 to 75, I believe. Yeah. And that will be the position that the servo arm will move to. And you might find to calibrate it, you do a little equation, a mathematical equation to get a number that fits into this range from 75 to 225. And then stepper motors, we need to play around with the hardware of those. We need the 4-pole motors. Again, we've got one working in the workshop to give you an example of how to do that. But yeah, you'd have to have a particular, depending on the stepper motor, you'd have a particular sequence of outputs to determine where the position is. So it might just have a 4 output position. Some of them have 3 outputs. But yeah, example of that. Pulse. Now, this can be for more advanced sending out signals to other bits of hardware. These are actually quite versatile and up to date as well in terms of how you can communicate with other devices. It's slightly more advanced. I'm not going to cover it in this tutorial, but yeah, certainly the support's available from New Wave Concepts to be able to output to a different device and communicate. What this can be useful for though is it's a good example of what's called parallel processing, which we'll come to in a minute. So in other words, the circuit we're designing, this flowchart, if you imagine drawing this all out, it's just one step at a time. So if I've got a wait command here, nothing really is happening whilst it's just paused for 3 seconds or something like that. I might have a light flashing on and off, and then I go and do something else, but I still want the lights to flash on and off. And again, I've got an example of that in the project I'm going to show you an example of. So you can have, let's say, every half a second, 500 milliseconds on output 1, we will send just a little tiny blip like that, and you can have a little light flashing or something like that. PWM, I keep mentioning that, it's basically a means of communicating to something like a servo or like a dimmer switch or something, an analog output into a digital output. Basically, it's just on and off really quickly. So you can choose the shape of it depending on how big a kind of high in that 500 milliseconds each one of them are. Or, for example, you can do your own pattern. So you can have as many outputs as you want, flashing repeatedly. So in this case, it would be repeatedly just alternating between outputs here every half a second. So this will just carry on for as long as the pulse is switched on, even though something else is happening down there. It'll still be pulsing. So it's a good way of kind of having two things going at once, certainly two outputs going on at once. Now, I try not to digress too much to be able to kind of come back to where we're going through this list of things, but that's parallel processing outputs. You can also have a parallel processed input, which is basically an interrupt. So any time I press a button, doesn't matter where you're reading, whether you're reading that button like with a digital read at that point in the flowchart, at any time during that flowchart thing where I've got an interrupt, say whenever D0 is pressed, then it's a little bit like a subroutine. We have a string of stuff going on here until this command. So everything that happens within these two commands will happen whenever D0 is pressed in the main program. That's really useful, and again I've got that as an example in the project. So yeah, two ways of doing parallel processing, things happening outside of the bit your flowchart is on at the moment, which is it's a good workaround, and it is actually quite a limitation of many programmable circuits. Certainly more advanced ones like Arduinos and stuff like that have that problem of programming two things at once. So yeah, pulse we just covered. Count, so you can send out a signal, how many pulses are happening at the other end, you can count. Now again, in the example project I've shown, I've actually got two PIC chips running simultaneously, and one sends the signal out to the other one. It's just an easy way of kind of having parallel processes happening separately. Infrared in, infrared out, again, kind of more advanced. If for any reason you want to have a remote control system in your project, then we can look into that. And again, serial in, serial out. You can communicate with a computer with your hardware, just sending a signal via the serial data, which is actually what a lot of the Genie chips, certainly on the old computers in A10 and in the workshop, communicate with a serial port, which is a bit like a USB. It's just a much more old-fashioned primitive version. I2C is a communication language, as it were, with many different types of LCDs and all sorts of things. You come across this quite a bit in Arduino programming as well. But the great thing about it is you can have many different peripherals, so bits of hardware connected to your PIC, and they're all communicated on the same output. So there's a pulse given out with a certain address. So it says, okay, send this signal out to the LCD, and you can have big fancy color LCDs and all sorts of things like that. They've all got an address, so you basically assign a certain device connected to that one output, and you say, okay, this is the message for the LCD, and then on the same line we're going to send another message to the motor or whatnot. It's advanced stuff, and to be honest, I haven't really covered it that much in Circuit Wizard, but if there's any reason why you want to have stuff like this, then certainly the support from New Wave's the software developer New Wave Concept is quite good. And again, there's ultrasonic rangefinders as well as kind of means of getting an analog input to determine how far away an item is. So you can have some pretty kind of advanced products with kind of quite advanced programming solutions here. Wait, simple command we've covered already. Pause, like a tiny version of that. Sleep, to be honest, yeah, you just kind of turn the program off at this point and save power. It's quite useful if you've got batteries on a device that you want to leave on for a long time. So you don't want to have the program doing much until an input's pressed. And then a very useful thing, obviously, is a timer. This just simply counts in whole seconds, and it goes up to 255, which is the number of bits that the program stores, basically. So again, I've got an example of this, how it happens in the project that I'm going to give an example of. So I might actually split this video into two halves, certainly because I just get one take on recording it. So if I make a mistake, it'll be annoying having to do this all again. And then really useful thing here is expressions. So basically we've got the top one is the most versatile one here. So remember I was talking about variables. So at the beginning of a program, let's say our score is going to be A. I'm going to say set the score to 0. A equals 0. So that means the memory during the program running, unless we do anything to this variable, it will just stay valued at 0. So for example, the LCD, don't know if it's still on the page, but remember where I put score equals square brackets A, it will just say score equals 0. Now, let's say if a button is pressed, it gets 5 added to it. So we use the expression thing like that, and we say A equals A plus 5. Okay. Or let's say the score is A, but that's determined by how long it took. So let's say, as an example, if you took 10 seconds to press the button, you get no points, whereas if you press the button instantly, you get 10 points. Then all you do is A equals time, or sorry, A equals 10 minus time. Like that. So you've got a really powerful kind of versatile way of calculating stuff. So as well as the basic arithmetic things, you've got percentages and then logic here. So you've got and not exclusive or exclusive or all sorts of things here. Again, they're quite kind of specific functions that you might want to deal with in individual projects, whatever you do. So yeah, there's lots of things here, just like with the analog where you can set individual outputs to high or low. You can do them all on this as well. So a lot of these buttons are pretty pointless because you can just do it in the expression button. So for example, increment would just be a equals a plus 1, which you can write here, or decrement a minus 1. Something you can't do on this is random, so this is a useful thing. If you want to just throw out a random number from 1 to 10, then you choose 1 to 10 here, variable a. Scale, I remember I said it deals with whole numbers. You can have scale factors here, something you can't do in the expression thing, because you can only write whole numbers in the options here. Whereas if you want to say enlarge something by 140%, 141%, then you just say scale by 1.4. Okay, so you can have fraction decimals there, and then clear or set. Again, you could have a equals 1 in the expression thing to do the same thing here. Clear, you can have a equals 0, and then swap. It's pretty self-explanatory there. Again, we'll look at this in more detail as and when, if you want to have a slightly more advanced, you know, storing data, for example. And again, you can save out data, because if you switch this chip off and on again, it loses everything that has happened during the program. But if you want to store data out to another piece of hardware, you can do that here. Again, it's slightly more advanced stuff, and Rob Winter in other videos covers a little bit there. But yeah, just a quick little overview of what we can do in the program. We've looked at the events and interrupts. And by the way, you switch they're kind of constantly looking for the input. You can switch it on and off in the circuit with this one here. So if you click enable, so in this case the events and the interrupts are numbered 1 to 5. So this one is number 5. So if I want this interrupt to happen, then I'll say enable 5. It'll say 5 enable, and then it's constantly looking for an interrupt on, you know, input. Let's say on this one, this input 6. And then when I want to stop looking for that input, I'll just use disable. So copy and paste that, and then uncheck that, and it's disabled. Ooh. Okay, so that means this interrupt will no longer happen. So yeah, quite a powerful load of different options you can create, and yeah, so hopefully it will give you an idea what you might be able to do. Remember thinking about all the bits of hardware as well. So here, for example, we've got a relay as a kind of bigger output to control something a bit more beefy than one of the tiny little motors that you can plug into the Genie chip. Say this is a 12-volt pump or something like that, and it might be a light sensor. So we've got LDRs, light dependent resistors. Remember your potential divider theory that we've covered quite a bit. So this is basically tied in with a resistor. Now I should be drawing it here. And you'll notice what I mean about the fact that when you've got a schematic chip, or rather a chip that's as is with all the pins in the positions that the real chip is, it becomes a little bit muddled when crossing wires and stuff like that, because if we're going to have an output 1 between these two as a potential divider, see what I mean? It's just a little bit of a muddled way of doing it. So what's this going to look for? Well, it's going to have an analog input from 0 to 255, so 0 being 0 volts and 255 being 5 volts, the full input voltage. And we might actually want to have a variable resistor here, because you can adjust the sensitivity. Now, how many of you can remember which way round an LDR is? When it is bright, my little kind of way of remembering it is think of chocolate. It sounds like a really kind of weird way of thinking about it. It works as well for thermistors as well, the same kind of thing. So whereas instead of light, we're looking at heat here. So when it's hot, chocolate melts. The chocolate flows, current flows. So therefore, it is less resistance. So basically, when things get hot, they're less resistant. When it gets bright, think of a sunny day, the chocolate melts, it flows. That's my little kind of weird mnemonic, but it's just a handy way of just remembering which way round it will go. So if light is in this case here, if light is shone on this LDR, we're going to have a small resistance there. So therefore, this is going to be a higher input there. And then if we swap it around, it's the other way around like that. So it's just an easy way of remembering which way around it goes. And remember also, if we put a variable resistor here, we can just adjust the sensitivity of that. So this might be a, you know, this is the simple circuit design for, let's say, your garden pond that comes on in the daylight, for example. Whatever. So yeah, we've got infrared receivers, we've got ultrasonic rangefinders, so you can detect, you know, you could even make a quite an advanced parking sensor with this kind of electronics. Yeah, so quite a few inputs to play with. Like I say, these sensors are all quite useful in your projects, and then outputs, lights, motors, LCDs, servos. Hopefully some of you might have kind of taken on what you've learned from the mechanisms in the pet feeder project to create something that, you know, has a bit of mechanics in as well, so it'll actuate and it'll move something in quite a nice, effective solution. It's a good solution, for example. So yeah, enough of me ranting on about what you can do with Circuit Wizard. Hopefully, showing you a few of these features might help you at this stage kind of draw upon any ideas and ways of solving a problem during this stage of your NEA. In the next video I'm going to do shortly, give you an example of all these features in something that I've done. Okay, thank you very much.